Why you should care about entropy? Well, entropy gives us insight about how much information is contained in a message, a data point, or even an event. This concept is essential for understanding why some machine learning models are effective at processing information, predicting outcomes, and ultimately making smarter decisions. In this video, we are going to dive deeper into the topic and understand the mathematical intuition behind entropy. At the same time, we are going to try to explore the connection between information theory and machine learning. Before starting the video, it is assumed that the viewer has some good foundations into the mathematics for machine learning. And for those of you who might find some of the mathematical concepts I explain a bit difficult, I recommend you as a starting point the Mathematics for Machine Learning book. Alright, we'll begin with a general example. Let us imagine that we have a random variable x and we try to quantify the amount of information we receive by observing an event. And you should interpret this amount of information as the amount of surprise we have when the event happens. Let us begin with a very common event. Let's say that the event we analyze is today it rains in London. I moved recently in London, and for those of you who live there, you might know that most of the time it's quite cloudy and the chance of raining is quite high. I did not check the statistics, but for this example, let us imagine that the probability is above 0.5. It's a highly probable event, so this event is not surprising, which means that it doesn't offer us a lot of information. Alright, in the other corner, let us take a very improbable event. So today it snows in Madagascar, and the probability of this event to happen is extremely low, if not zero. And this event itself is quite surprising, which means that it offers us a lot of information. It is clear from now on that the amount of information we receive depends on the probability distribution P of x. Therefore, we are looking for a monotonic function which depends on P of x, which would quantify this amount of information. And the respective function is the minus log of P of x. If we look on the plot from the right side, we can notice that it respects the monotony we are looking for. The less probable an event is, the more surprising it gets when it happens, so the more information we are supposed to receive. And the more probable an event is, the less surprising it is when the event happens, so we should receive less and less information. Now let us imagine that we are trying to send a message to a receiver. Assuming that we still work with discrete random variables, the average amount of information sent to the receiver is equivalent to taking the expectation with respect to our formula h of x. This result is the entropy of a random variable, or the Shanon entropy to be more precise. Fun fact from Bishop's book: it is said that von Neumann recommended to Shannon that he use the term entropy, not only because of its similarity to the quantity used in physics, but also because nobody knows what entropy really is, so in any discussion we will always have an advantage. There is one more important detail that we need to take into account. We should notice that the limit when the probability goes to 0 is equal to 0. So from now on, we are going to take P of x log of P of x equal to 0 whenever the probability is equal to 0. One more thing that is important to mention is the base of the logarithm. The base 2 is chosen because the unit of the entropy are the bits for the binary digits, and we are going to see why in the following examples. Let us now imagine that we have a random variable which is simulating a dice, and we know that a dice can be modeled as a random variable with 6 uniform states. If we apply the entropy formula, that means that the entropy of the dice, or the average information we transmit to a receiver, would be approximately 2.5 bits. It does not seem a lot at first sight, but things will change when we look at the second example. Now let us consider non-uniform random variable, and let us assume that these are the probabilities of these states. In that case, the entropy will be equal to 2 bits. And if we look once again at the previous example, we have distribution with more states, which has a lower entropy compared to a random variable that has less states, but it has a uniform distribution. The reason why this happens is that we can take advantage of the non-uniformity, and we can allow shorter codes to states which are highly probable. In that case, it means that The most frequent states will receive codes or with less number of digits, like the case of A, which occurs in 50% of the cases. With the downside that we offer longer code lengths to states which are less frequent and less likely to happen. The key insight you should take until this point is that distributions which are big to just a couple of states will have lower entropy. Meanwhile, distributions which are flattened and they have almost equal probability to most of the states will have higher entropy. The maximum entropy configuration can be found by maximizing H, which is a constraint by Lagrange multiplier, in order to enforce the normalization constraint of the probabilities. And that's what we are going to do right now. We will begin by firstly rewriting the entropy function so that it contains the constraint of normalization with the help of a Lagrange multiplier. Now we are going to look for the stationary point. The first term is going to be derived using the product rule. And the second member should be easy for everyone to derive. We are working with stationary points, so the derivative in a stationary point should be equal to 0. And we end up to an interesting result where p of xi is equal to a constant. If we take into account the fact that the distributions are normalized and we replace the value, we end up to the following result. And that means the maximum entropy appears when we have a uniform distribution. If we also replace this value into the entropy formula, it denotes that the maximal entropy is equal to log of n, where n denotes the total number of states. I can imagine that for many of you this result would have been obvious, but I believe that it is beneficial for all of you to try also this analytical exercise and convince yourselves. One more thing which is important and I omitted is to check that the respective stationary point is also maximal, and you can do that by taking the second derivative. Right, so we've covered Shanon Entropy and how it measures the uncertainty or the average surprise of a random variable. But in machine learning, especially when we are training models, we often need to measure not just the uncertainty of one distribution, but how well one distribution represents or predicts another. That's where cross-entropy comes into discussion. Cross-entropy builds on Shanon entropy by comparing two distributions, the actual true distribution and the predicted distribution. It measures the expected number of bits required to encode events from the two distributions if we were using the predicted distribution coding scheme. By doing so, cross-entropy gives us a framework to quantify the discrepancy between what we know to be true and what our model believes. Let's take a look at this graph, and let's imagine that f of x represents a true distribution that we try to match. Q1, Q2, and Q3 are possible predicted distributions. If we take a look at Q1, we can notice that the distribution is shifted to the right, missing the peak of the true distribution, and it has a cross-entropy of 15.79, which is relatively high. when we look at Q3, the red dashed line, although the distribution is similar in shape, it's more spread out and offset, and its cross-entropy is around 29.24, and it's the highest among all three. Q2, on the other hand, the green dashed line, this one is much closer to the distribution, aligning well with its shape and position. Its cross-entropy is the smallest among all of them, which is 7.31. The key takeaway is that entropy increases as the predicted distribution diverges more and more from the true distribution. In machine learning, we are rarely, if ever, given the true distribution P of x. Instead, we work with a data set, a collection of observed samples that represent the outcome of the true distribution. Let us see how we adapt cross-entropy for this setting. Suppose we have a data set of n samples, each labeled with a true class y, and the predicted probabilities from a model qy. We treat labels as observation from the true distribution Px, which we approximate using a one-hot encoding. So in this case, if xi is the observed outcome, P of xi should be 1 for the true label, and P of xi should be 0 for all the other classes. If we resume the cross-entropy to a single observation, then the entropy should be equal to this. Why is that happening? Because P of xi is equal to 1 only for the true class y, and the contribution from all the other classes is 0. Alright, for the entire dataset we need to compute the average cross-entropy over all samples, and this gives us the following configuration for the cross-entropy loss. Lovely. Now that we understand cross-entropy and how it measures the difference between our model's prediction and the true outcomes, we are ready to take a step further. So let us now talk about relative entropy. Consider some unknown distribution P of x, which is our true distribution, and suppose that we tried to approximate it with a distribution Qx. And now let us imagine that we try to construct a coding scheme for the purpose of transmitting a message x to a receiver. So far so good, but at the end of the day we would like to have something as close as possible to P of x. And we would like to measure how much additional amount of information we need to approximate P of x. The average additional amount of information required to specify the value of x as a result of using Qx instead of the true distribution Px is given by the following formula. This is known as the entropy, the relative entropy, or the Kullback-Leibler entropy, or the KL divergence between the distribution of Px and Qx. If we take a closer look, we can notice that this relative entropy is resulting from the difference between the cross-entropy and the Shanon entropy. One more thing that is important to be taken into account, and I'm going to pointing it from now on, is that the KL divergence of P and Q is not the same with the divergence of Q and P, so it's not symmetric. You could also think about KL divergence as a measure of how much information is lost or how much inefficiency is introduced by using our predicted distribution in place of the true distribution. Now we are going to prove that KL is greater or equal than 0 with equality when P and Q are the same. Alright, we are starting the proof. We will try to prove that the KL divergence is equal to 0 when the two distributions are the same. And for that we'll need to imply convexity. So a convex function f of x is one for which every chord lies on or above the function. And we can see that as well in the plot from the right side. If we do a proof by induction, we can show that a convex function satisfies the following property. This property is called Jensen's inequality. If we try to interpret the lambdas as the probability distribution over a discrete variable x, then the function can be rewritten as following. And since we work with continuous functions, we can also rewrite Jensen's inequality in the following form. everything we did was just to use the expectation formula for the continuous variables. Okay, now let's prove the property. The logarithm is a concave function, but because we have a minus in the front, this whole equation is a convex one, so we can apply Jensen's inequality. We can simplify the terms. Since we work with distributions, we also need to take into account that the integral of q of x should be equal to 1. And the result is equal to 0. Minus logarithm of x is a strictly convex function, so this equality holds only when p of x is equal with q of x. Like in the case of cross-entropy, we're never going to be provided with the true distribution. In general, we are going to be provided a data set when we work with machine learning projects. So now let us make the connection between the KL divergence and the data set. Let us imagine that we have a data set generated from an unknown distribution p of x. We wish to model it, and we try to approximate this distribution by using some parametric distribution, which we are going to note it as qx theta. You can think about any kind of model which is governed by adjustable parameters theta. So one way in which we can determine the parameters is to minimize the KL divergence between the model and the distribution. We cannot do this directly now because we no longer have p of x. Okay, but suppose that we have observed some training points. So we have some training points xn, which we drew from the distribution p of x. The expectation with respect to p of x can be approximated by using the finite sum over the points. Alright, so we are going to begin by decomposing the KL divergence. We are going to split it in two parts. Okay, and now we are going to use the finite sums for the two components. The second term on the right hand side is independent of theta, and the first term is actually the negative log likelihood function for the theta parameters under the distribution of the chosen model. Therefore, we see that minimizing the Kullback-Leibler divergence, the KL divergence, is equivalent to maximizing the likelihood function. We got to the end of this video, so let's wrap it up one last time. We started with Shanon Entropy, which gave us a way to measure uncertainty or the average surprise in a probability distribution. Then we extended the concept even further with Cross-Entropy, which measures how well one probability distribution aligns with the true distribution. Finally, we introduced KL divergence, which bridges these two ideas. It's the extra cost or inefficiency when using an approximation distribution instead of the true distribution. If by any chance you consider this video useful, don't forget to give a like, a share. Feel free to write me in the comments what you liked, what you didn't like, what you would like to see as improved, possibly what other concepts you would like me to cover for you. It's not so simple to do YouTube videos, but I'm trying my best to improve, and I'm pretty open for feedback. That's it for today. Thanks for watching, and until next time, keep learning the mathematics. Mathematics for Machine Learning.